Hello friends, welcome back to this second part of the UPBD method for frame-SHEAR wall buildings. In this part we shall be discussing the theoretical background of this method. We have discussed earlier that the UPBD method can consider more than one target performance objectives, namely drift and performance level. Of these two, performance level is more important because it designates the damage in the structure, and the damage we want to control to a degree which is suitable to the functional requirement of the structure. So we shall be following the reference given here, performance by seismic design of hospitals, PhD thesis by S. Choudhury, IIT Roorkee, 2007. So here is a multiple degree of freedom system. These are the shear walls symmetrically disposed on the peripheral sides of the building, and this can be converted to an equivalent single degree of freedom system that we have discussed earlier in connection with other methods. So equivalent single degree of freedom system will have equivalent mass ME, equivalent height HE, and equivalent stiffness KE. Now this system we have considered when it is undergoing a displacement, a rotational displacement. The maximum displacement is theta d, which is our design drift. And this theta d comprises of two parts. One is elastic part and the other is plastic rotational part. The elastic part is theta yw, the maximum yield rotation of the wall. Maximum yield rotation means this is the elastic rotation, after that plasticity will start. So beyond theta yw, the elastic rotation, whatever rotation is there, is plastic rotation. Now in the FEMA documents, the values of plastic rotation theta pw are given for different performance levels like IO, LS and CP for structural walls. So this we shall be utilizing to make a formulation for this UPBD method for dual system. We assume that the entire plasticity arises out of the shear wall alone. Actually, the plasticity will be arising out of the shear wall as well as the beams. Due to capacity design, column will not form any plastic hinge, so they will be elastic. However, the shear wall is a very deep beam. It is also a beam. It is a cantilever beam, deep beam, and because of its depth, large depth, in comparison with the depth of other normal beams, it can dissipate large amount of energy, so that we can assume that the entire plasticity is arising out of the shear wall alone. So if so, the theta d, the total plastic rotation, which comprises of the elastic rotation theta yw and the plastic rotation theta pw, that is the plastic rotation as shown here is arising out of the wall only. That is what is the meaning of this equation 1. Here theta d is design drift, which will be given to the designer. Theta yw maximum yield rotation of the wall and theta pw plastic rotation of the wall corresponding to the performance level for which you are designing. So we take the equation number 1, theta d equal to theta yw plus theta pw. Theta yw is available in the literature. It is phi yw hinf by 2. Hinf is the inflection height of the wall. This we have discussed in connection with the DDBD design for shear wall systems. So these are clear. So phi yw is the yield curvature of the wall and IHNF inflection height of the wall. So what we do with this, let us give the expression for phi yw also available in the literature. So phi yw available in literature is twice epsilon y by Lw. So if I put equation 3 in equation number 2, then I get this theta yw. In place of phi yw, I am putting twice epsilon y by Lw. 2 and 2 get cancelled. 2 is in the denominator here and 2 is in the numerator here. So they get cancelled. I get epsilon y hinf by Lw. So this is my equation number 4. So 4 can be put in 1 because in 1 we have theta yw and theta pw. We are not worrying about theta pw because that is available in the FEMA documents. We are worrying about the expression for theta yw. So now theta yw we have got as equation 4. So this we are substituting in equation number 1 and we get it like this: theta t equal to epsilon y h I n f by LW plus theta PW. So this can be rearranged. We are interested in the length of the wall LW, so we take it on the left hand side and we get this grand expression LW equal to epsilon y h I n f divided theta t minus theta PW. Now this is the length of the wall, the horizontal length of the wall, which will be giving you a building which will satisfy the drift theta d and satisfy the performance level corresponding to the value of theta PW you have chosen from the standard documents. Now how to get the thickness of the wall? Let thickness of the wall be TW. Suppose BT is the total design force in the direction concerned, that is the direction of the earthquake. This total design force will be taken by the frame and the shear wall together in some proportion. So it is assumed that the frame carries about 25% to 30% of the total shear. So BF is known in the beginning as a fraction of total. BW is the shear carried by the wall. So BW equal to BT total minus BF. Now say NW is the number of shear walls in the concerned direction, that is the direction of the earthquake. Shear carried by one wall which shall be designated by BW1. So it is BW, the shear carried by the all walls in that direction, divided by number of walls in that direction. Remember, the shear walls in one direction only will be activated at a time when earthquake is taking place in that direction, and other directional shear walls will remain silent. So BW1 is the shear carried by one wall, is total shear carried by wall in that direction divided by number of wall in that direction. A simple philosophy. Now shear check you have to apply like this: this BW1 divided by effective area of the shear should be less than maximum permissible shear stress in the concrete. So BW1 divided by 0.8 LW. In certain code like IS code, it is given that 80% of the length of the wall is effective in carrying shear, and this is the thickness of the shear wall. So this gives you the shear stress induced, and this should be less than the maximum permissible shear stress in the concrete given in the code. So now for further design, the shear carried by the concrete alone is given by tau c into the area of the shear wall in shear. So tau c into TW 0.8 LW. This much shear will be carried by the concrete. So remaining shear Bs is equal to BW1 minus Bc is the amount of shear in one wall to be carried by stirrup or horizontal steel. So spacing of the bars will be given by simple formula 0.87 Fy A tie into D by Bs from here. A tie is the area of all the tie legs of the shear reinforcement. Generally 2 legs will be there because shear wall thickness is not very large and you cannot accommodate more than 2 legs. So it is indicating area, cross-section area of 2 legs of the stirrups. So spacing is obtained, so you have also designed the thickness of the wall and the corresponding steel in the shear. Now the theta PW we had been talking about are given in the FEMA 356 and also in SCI 41 document. In using SCI 41 document, one must be very careful that in the SCI document the difference between the primary members and secondary members have been given in a cumbersome way, and it creates confusion. So it may be safer to use the FEMA 356. So it has a steel ratio including the axial force in the wall divided by the TW, LW and FC dash, the area of the wall and the concrete. So this is a stress ratio in the wall and the values are given here, and there is a shear stress which is horizontal. So amount of shear divided by TW, LW, FC dash is the shear stress. So corresponding to different values, the IOLS CP values are given. Now whether the boundaries are available at the end of the shear wall, this is what is given here. So we are considering confined boundary boundary walls are given, or it has been confined by giving additional vertical steel, horizontal steel in the ends of the wall. So this condition conforming is considered here. ABC we don't require. These are the nonlinear response parameters required in the computer program. We are concerned with the plastic rotation under IO, LS and CP. These are given for primary and secondary members. So basically shear wall is a primary member, so we shall be concerned with these first three values. Now while designing in the beginning, you do not know the stress ratios, this column or this column. So what tricks we apply, we take average of all this so that everything is included in some way. So we take the average of the IO here, this was radian, average of the all LS4 values here, and average of the CP values here. These are your theta PW, the plastic rotation of the wall, to be used in design depending on whether your building is IO building, LS building or CP building. Now we try to understand the significance of this equation LW equal to epsilon y HINF divided by theta D minus theta PW. So for this we make it non-dimensional, we divide it by HINF. So LW by HINF is non-dimensional term is equal to epsilon y divided by theta D minus theta PW. So this we shall plot as a variation of theta D. Theta PW is constant for a given performance level of the building. Theta D shall be varying, and we shall get a plot of this. So this plot is shown here. So in the horizontal direction we have the theta D, and vertical direction we have this LW by HINF ratio. Here we make an assumption what theta D should be conforming to IO building and LS building and CP buildings. So considering some suggestions given in the FEMA documents and other documents, we consider IO to be say 1% to 1.5%. You can also say IO to be 0 to 1.5%, but 0 to 1% level is very stringent and may not be required in all practical buildings. So we start with 1% drift and finish at 1.5% drift, which covers the range for IO buildings. Similarly, LS buildings are covered from the drift of 1.5% to 3%, and the CP building from 3% to 4%. Okay, so this is some suggestion we take from the documents and some intuition we apply to categorize these divisions of the drifts for different performance levels. Okay, now we put here in this equation epsilon y is Fy by Es, the yield strength of the steel divided by the modulus of elasticity of the steel is epsilon y. Theta D is your design drift, and theta PW you take as per the performance level the plastic rotation of the wall. Suppose I take theta PW corresponding to the IO level of plastic rotation. Then theta D I can vary and I get some numerical values on the right hand side, and left hand side is this. So from here to here if I vary, I get this curve AB from 1% drift to 1.5% drift, AB. Fine, there is no problem. Similarly, I put the plastic rotation corresponding to the LS level and plot it again, varying the theta D. Theta D will now vary from 1.5% to 3%. So we get a line CD. Okay, so there is no problem in this getting the line. Similarly, for the CP building, you can put CP plastic rotation here and get the line EF. Now some more information is required, some more understanding is required for this diagram. Now suppose your building is here in the LS building you have chosen, and you are here, that is LW by H inflection is 0.25, you are here. So if you design a building for LS with this LW by HINF ratio, that is certain value of HLW, then you are getting a LS building, but with the same depth you can also get correspondingly here the IO building. So why should I put extra cost in the LS building which can give me directly IO building? So this part I shall consider as only IO, and this part we shall discard. So C to M I shall discard by drawing a horizontal line from the point B. So BM is horizontal line, and CM I discard in the LS category of buildings, and remaining line MD will give you the LS range, including from B also. So under curve BMD, whatever is hashed will be LS buildings. Similarly, if you consider the CP building line EF, then any range here for a corresponding length of wall will give you a building also lying in the LS line here. So instead of using a CP building here, with the same cost I can get a LS building. So I draw a horizontal line from here D, touching here at N, and this part EN I shall discard for the CP building, and CP building will be covered by DNF and its extension here. So if we have understood this logic, then we take another case of this dotted line. How it is obtained? We put here theta PW equal to 0. When theta PW equal to 0, it is a elastic condition, elastic. There is no plasticity. So theta D I can vary from 1% to 4%, and I get this line PQ. So this dotted line PQ indicates the elastic condition of the wall. Okay, and if you go above this line, then you are entering into plastic condition of the wall. More you go upward, more plasticity will occur in the wall, but you cannot go beyond this upper bound, which is given by A, B, M, D, N, F line. So between this upper bound and lower bound, you have this hashed area, which is the bellied zone for the length of wall LW. So suppose you take a length here, this is also LS because we are in the LS zone. If I take a length of wall here, then also it is LS. Now which one you shall take? Generally, if you take on the higher side, then and all the wall length will be going to plasticity, and that will be economical. If you go on the lower side, then a small part of the wall will be going to LS and remaining part will remain elastic, so that will not be economical in that case. Anyway, a safe zone is the hashed area zone. So hashed area zone indicates the viable zone of design. Okay, now here is the inflection height explained through diagram. We have understood this in previous videos in connection with the direct displacement based design of dual system. So the frame bends with this convexity on the right hand side. This is called shear bending, and the wall bends with this convexity on the left hand side, which is a cantilever bending. Both these are monolithic, so they will finally take a position of some average interaction between these two, and after interaction you get a bending moment diagram like this. The wall bending moment diagram changes sign, having a point of 0 bending moment here, which is the point of inflection. And this is the frame overturning moment. If you put a unit load here, then 1 into the height will give you this value of the frame overturning moment for the purpose of initial design. These are not final values. Similarly, wall bending moment also shall be doing like this, distributing say unit load over different floor levels and finding the bending values in the wall. That will be good for the design purpose. Now, how the moment etc. are calculated for the wall, this we have discussed earlier also in connection with the DDBD method for dual system. Any overturning moment in the wall equal to overturning moment in the previous floor level plus a multiplication of the previous floor level shear into HI minus HI plus 1 minus HI, that is the height of story of that level. And the wall moment MWI is given by wall moment above the story, in the above story, multiplied by the shear in the story above into the height of story. So these levels are shown here, I plus 1 level and ith level between any two floors. Now you have to make a table, as we have discussed earlier in connection with DDBD for dual system, to make a table for finding the inflection height H, I and F. So you put a floor number, the height of floors, masses, which are to be known at the beginning. Masses will generally come out of the floors which you already designed, columns which you will take maybe slightly approximately in the beginning considering the capacity design. So these values are known, HI, MI, and then find the product, then find the summation divided by, so this product divided by summation of the products. And BTI calculation we have discussed, MOTI calculation. BF is considered constant. Suppose the designer decides that 25% of the shear will be carried by the frame, then BF will be simply 0.25, 0.25, etc. because we are initially distributing unit load in the frame and shear wall. So BF will remain constant, say to say 0.25, and BW you calculate as per the formula discussed in the just previous slide, and MW as discussed in the previous slide. So if you put this column BW, wall moments, then you'll get a 0 point where wall moment is 0, and that gives you the inflection height HI and F. Now you have to get the displacement profile of the wall. Earlier we had got displacement profile for the frame which are simple, but in the case of wall you have to consider the yield displacement of the wall. This was suggested by Sullivan et al. In 2006. So yield displacement in the wall in the ith story will be given either by this formula or the second formula, depending on whether the height of the story is more than inflection height or height of the story is less than inflection height. So seeing this height level, I can use this formula or this formula. All other parameters are known here, phi YW etc. are known. And then finally the displacement of any floor is yield displacement of the wall as here, plus a parameter guided by the drift of the design, yield curvature of the wall, inflection height, and height of the current story. So this is the displacement of the ith story given by this formula, where we are using delta IY from the above two formulae. Now once the displacement profile of all the floors are known, you can simply use this formulae which are familiar with us by now. The design displacement, summation mi delta I square divided by summation mi delta I. Similarly, effective mass, summation mi delta I by delta D, and effective height, summation mi delta HI divided by summation mi delta I. So out of this delta D will be required in the final calculation of the base shear. M will be also required for calculation of the effective time period. Now we find the ductility in the system. Ductility will be there in the frame and ductility will be there in the wall. From the ductility we shall find the damping. From the damping we shall be finding the effective time period. So frame ductility is given by this simple formula, delta I minus 1 divided by HI minus 1 multiplied by 1 by theta YF. Theta YF is the yield rotation of the frame given by 0.5 epsilon y LB by HB. LB is the length of beam, HB is the depth of beam. So in the frame, beams are there which undergo ductility, undergo plasticity. So the beams are only involved here. This is length of beam, depth of beam. So there will be as many values as the number of stories, and then you can take a average value of the ductility of the frame. We have discussed this calculation previously in the DDBD method. Now we go to the wall ductility. In the previous slide we found the frame ductility. The wall ductility is given by this expression mu w 1 plus 1 by LP phi YW theta D phi YW HI N F by 2. Here only new term is LP. LP is the length of plastic hinge. Phi YW the yield curvature we have already seen, twice epsilon y by LW. So LP is given by two expressions here. One is 0.022 Fy dB. dB is the diameter of the bar in the wall, the vertical steel diameter dB, and inflection height is involved. And the second expression, 20% of the length of wall and 3% of the height of inflection. So out of these two expressions, whichever is smaller will give you the LP. What is LP? Is the height of plasticity as in the distributed plasticity. Plasticity can be considered as lumped in single point, or it is really actually it is distributed over a particular physical length. So that length is available in the literature given by this. So substituting this, you can get the value of mu w. Now system ductility, we have got the frame ductility mu f, we have got the wall ductility mu w. How to get the total system ductility? So mu ESD, we are putting this symbol for system ductility, MW mu w, MW from that table we have discussed, MOTF also from that previous table. And so MOTF mu f divided by MW plus MOTF. So this will give you the system ductility. Now we have to find the damping. Damping is there in the frame given by this expression. Sorry, start. We are familiar with this expression in connection with the DDVD method for dual system. So mu f already calculated, mu w already calculated, you can use. There is a new term here, T trial, and a term R. R is called the post-yield stiffness ratio. That is, after yielding, what is the stiffness divided by initial stiffness, that ratio. Generally it is 0.5 to 0.05 to 0.1, that is 5% to 10%. T trial is given by an expression n by 6 mu ESD. Mu ESD calculated in the previous slide. N is the number of story in the building. So this is approximate value of the T trial. If final value of the T is not matching with this, you have to make another round of calculation. So the system damping now, overall damping in the system comprising of the wall and frame is given by this expression, MW JW from here, MOTF JF from here, divided by MW plus MOTF. So this system damping is important to us now to calculate the effective time period in the system. We plot the displacement spectra for the design spectrum you have considered. In this diagram, the EC8 design spectrum has been considered at level 0.5 G. The red line is the 5% damped demand line, 5%. Displacement line corresponding to the 5% damping. And this is the damping corresponding to the value we have just discussed. This damping, Xi ES DOF. So this calculated, there is no problem now. So this black line is corresponding to the damping Xi ES DOF. That is damping of the system. Now delta D we have calculated earlier. You draw a line at delta D horizontally and go up to this displacement spectral line, black line. Then drop particle downward, come to this time axis, and whatever time period is the effective time period TE. Okay. The computation, the drawing of the displacement spectra we have discussed in other videos earlier. So KE is involving this effective time period T. K equal to 4 pi square ME by T square. So here you are utilizing the effective mass of the system and effective time period calculated as here. So this gives the effective time period of the system, and the base shear is very simple from force displacement relationship, BB equal to K into delta D. K is 4 pi square ME by T square. Now this base shear is to be distributed over the floors. So if the number of stories is less than 10, this is the distribution formula. If the number of stories is more than 10, then first you distribute 90% of the base shear over all the floors, and at the roof level you add that additional 10%. This is done to take care of the higher mode effect in the system. Thank you very much for coming with me up to here. So please subscribe the channel, like and share the video, and give your remarks about the presentation, about the quality, and put your queries regarding anything in the comment box. I shall be glad to answer those to the best of my ability. Next video we shall be taking on the numerical application of the same thing. Thank you.